Hi, I'm Carl from the Internet of Bugs, and today's books, I could pick a lot of them. Let's try The Search, Building Search Applications, Lucene in Action, and Foundations of Statistical Natural Language Processing. All of those books are fairly old, so I don't know that any of them I would particularly recommend for someone who's just trying to get into the field. But that's kind of the point of this video, is that a lot of the stuff we're talking about today is actually really old. So for those of you that are new here, I've been a software professional for 35 plus years now. And this is my more technical channel where I talk about understanding and applying the technology and profession of software. This video is about large language models as a new form of big data search. And just to clarify, when I say large language models in this video, I'm just talking about the inference part of large language models. In other words, how large language models behave when they're responding to a prompt. There are a bunch of other aspects of LLMs, like the way they're trained and agentic loops and a bunch of other stuff. That's all beyond the scope of this video. I'm just talking about inference here. Also, this is not an LLM internals video, so I'm going to be oversimplifying and talking at a very high level about what the LLMs actually do under the covers to keep things moving. If you want an explanation of how they work, see the LLM playlist at 3 Blue 1 Brown. I'll put a link to it below. So let me anchor this video with a quote from the CEO of Anthropic, which is, "People outside the field are often surprised and alarmed to learn that we do not understand how our own AI creations work. They are right to be concerned. This lack of understanding is essentially unprecedented in the history of technology." So this quote, as far as I'm concerned, is utter BS. This quote is from an essay. I'll put a link to that below. And the quote surfaced recently in an AI doomer video that was full of this kind of garbage. I might end up doing a response video to that at some point. It might not be clear, but there are actually two somewhat unrelated piles of BS in this quote. The first is the "we don't understand" part, and the second is the "essentially unprecedented in the history of technology" part. So let's talk about the "do not understand" part first. So there are two high-level interpretations of their AI creations in this quote, as he calls them. He, and a lot of people in the AI space, from what I can tell, pick a particular interpretation that seems overly complicated and unnecessary to me. I find that there's a much, much simpler explanation. The dispute can be looked at as a disagreement about what does or doesn't count as AI creations. To them, it's a really, really unknowably complicated process that can't be understood. To me, it's a really, really simple process that's executed against gigabytes or terabytes of data that can't be predicted. We know how transformers work. We know what the algorithms do. We know that at a simple level, a prompt is encoded into a bunch of vectors. Those vectors are multiplied against lots and lots of matrices that were created during the training process to produce a result. And then that result is decoded back into words or images or whatever. The part that we supposedly don't understand is how the various matrix multiplications create the result. Except we do, well, kind of until we don't. An additional thing you need to understand is that there's a step inside the LLM inference where they literally insert randomness, although they call it temperature, saying there's no way we can understand why the LLM output did what it did when you know that you told it to make the output random. Is just deliberately disingenuous. The problem isn't that we don't know the mechanism about how all this works. The problem is that there's just way, way too many of these matrices to keep track of. We make a very small toy-sized neural network, and then we can figure out the whole thing. It's not very useful, but we can. Anthropic has even been able to find the Golden Gate Bridge neurons in one of its older, smaller models. I'll put a link to that below. The problem is not a lack of understanding, despite what they say. It's a lack of time. It's not impossible to trace through how a particular prompt was altered at every step along the way, passing through a trillion parameter model. It would probably just take so long that by the time we figured it out for one prompt, the model we just traced will have been deprecated already. There's nothing unknowable, impossible, or magical here. It's just so large that it's impractical to do. So another quote from that same article is, if an ordinary software program does something, for example, a character in a video game says a line of dialogue, or my food delivery app allows me to tip my driver, it does those things because a human specifically programmed them in. Now that is a mind-bogglingly dumb example, and bears no resemblance to what the LLMs do. A more honest analogy would be if 10,000 players are all connected to the same World of Warcraft server, and one of those players hears some line of dialogue. There are potentially thousands of different dialogue lines that could have been heard at that moment, depending on what was happening, who was where, etc., and the specific line of dialogue wasn't predetermined. It was chosen as a result of a series of interacting algorithms operating on all the data relevant to the player's game state and wouldn't have been able to be predicted in advance. Likewise, tipping your delivery driver is very straightforward. But for example, the process by which the delivery app determines which particular driver is going to be selected to be the one that's assigned to your order and which particular location of the restaurant that you picked it's going to go to can depend on dozens of factors, including where each driver is, what other assignments they've been given, what their rating is, what your rating is, how long it takes each driver to respond to the new order alert in their app, etc., etc. Once you get to a large-scale complex software system with lots of moving parts, many things just aren't predictable anymore. There are far too many variables that go into any given output, And a human just isn't capable of tracking all of that data in anything close to a reasonable time frame. Which leads us to the second issue, which is the unprecedented part. They say this because they want to interpret the trillions of parameters in the model as processes or code that we don't understand. Whereas I say that those trillions of parameters are just a huge data set that's too big for a human to track in anything close to a reasonable time frame. This kind of thing happens all the time. I've done several big data type projects, but I'm going to talk vaguely without going into any company secrets about 3 of them today. You don't need to memorize these. This isn't a test at the end, but just in case you're curious, here's kind of a brief overview of the different projects I'm going to talk about a little. One of them was for a company that remotely managed networks. We had a data warehouse that had network metric data, stuff like packets in, packets out, error rates, bytes, interface resets, that kind of thing, collected every 5 minutes or so for every one of millions of network interfaces across hundreds of customer companies. The next one was a data lake project, more on the difference in a bit, for a group that basically did supply chain management that tracked products and vendors and parts and shipments and such. And the last one was kind of a custom built thing, not strictly a data warehouse, not even a SQL database, but just a ton of full text indexes using Apache Lucene, which is a full text search library used for classifying web content. This is from a long time ago. The goal here is to show you how a lot of the features in large language models that people talk about like they're magic are really just extensions or evolutions of stuff we've been doing for years, or if not decades. Specifically, the inference step of querying LLMs is basically just searching against a big lossy copy of the information found on the World Wide Web. I'm not going to go into that here because I already talked about that in my other channel, link below if you haven't seen that video yet. So first off, let's talk about lossy compression, or more importantly, what happens when you need to present data that was stored in a lossy way. I'm talking about taking the information encoded in an MP3 file, for example, and turning it into signals to send to a speaker, or taking a JPEG file and making up the data for the pixels that weren't written down when the file was created, that kind of thing. For example, there are a number of steps that happen to turn an MP3 file into a speaker output, including Huffman decoding, requantization, inverse modified discrete cosine transform, inverse polyphase filter bank. You don't need to know what any of that crap is. Those steps don't matter for our purposes today. It's enough to understand that there are a set of steps that involve taking the relevant chunk of data from the MP3, running a bunch of algorithms and mathematical transformations on it, and then outputting the result. The thing that's missing in the MP3, or JPEG or MP4 case, is that these formats are not really intended to be queried. You just can jump around in time, and you can zoom in on particular parts of the frame, but that's about it. So let's talk about a warehouse full of network metric data. So as you can imagine, if you're collecting a few numbers for each of tens of hundreds of thousands of routers and switch interfaces every 5 minutes, and stuffing them all into a big database, the size of that database grows pretty big pretty quickly, and it gets really expensive to store all of it. So what we do is create what are called roll-up tables or aggregate tables, where instead of storing each data point, we store some summary, like an average or count or maximum of the points for a given time range. And the older the data are, the more you summarize. For example, 6-month-old data might be stored at 1 data point per hour. Year-old data might be stored at 1 data point every 4 hours. 5-year-old data may be 1 data point per day, et cetera, et cetera. Then, when it's time to display or report on that data, there are various options about what transformations or formulas can be used to do that. Oddly enough, on that particular project, the software package that we used to display and create reports for that data was from a company called MicroStrategy, which today they're better known for their position on cryptocurrency, but they actually used to make business intelligence software, believe it or not. Sometimes the reconstruction was straightforward, show me the network traffic from last December. There were a lot of more complicated things like capacity planning, or show me the network changes that are predicted to produce the best return on investment. We would frequently get bug reports from customers that they got a report that didn't make sense or that was truncated, and by the time we went and looked, it was working fine. There are lots of things that could be gone wrong, from MicroStrategy bugs to a database table that was locked or corrupted at the time the report ran, or it was unlocked or overwritten by newly inserted data by the time we got to the bug ticket. It was impossible to predict what it was that the report was going to say, and it was impossible to figure out what went wrong unless we stored a whole lot more data than we could afford to. There was just no way we could have done the calculations by hand to create any of those reports manually. The amount of data was just far, far too much for that. The data lake project, which is kind of like a data warehouse, except the data is constrained at query read time instead of at insert write time, led to a similar but much worse problem. To track the supply chain, you end up with thousands of suppliers who each have their own reports about their products, their receivables, their statuses, each one potentially in a unique format. These all get uploaded into the data lake on a semi-regular but often a predictable basis. Then you have to write code to tie all that data together to make your reports out of it. And any of those suppliers could have had any number of bugs or upload problems or software updates or changes that we hadn't been informed of. And a report that worked fine yesterday might get you completely different results today because somewhere the underlying data changed. Maybe it changed formats, maybe it was a redaction, maybe an error caused an upload to get truncated. And in theory, you could track down exactly what happened, but by the time you do, several other suppliers would have probably uploaded their new reports, and what you had might not have been relevant anymore. The full-text search project had a giant index that was trained on lots and lots of content that was categorized. For example, all of Wikipedia had been run through the indexer. Each page was classified by the hierarchy of Wikipedia categories associated with those pages. Some of the other sites that were either specific to a particular category, like news sites being classified by the section heading for that article, or one subject sites like a video game review site being all classified as gaming. Hopefully you get the idea. The idea was to take an arbitrary website that we had no knowledge about, without any human having to look at it, scrape the top few pages of the website and use that as a query to see what category that website would most likely belong to in our index and what text it would be like. Technically, it was find what category's content in the website in question was most similar to. We were running this, trying to classify hundreds or thousands of websites every day without a human ever looking at it. So this was in 2007, maybe 2008. So 10-ish years before the current transformer attention technology happened. So it understood words kind of, and to some extent phrases, but it didn't have any way to get the idea of context. So in other words, the vector embeddings of ChatGPT that now use the attention mechanism to tell the difference between whether the word right means in the sense of not incorrect or the sense of not left. Back then we had no such mechanism, so it would get thrown off a lot. It didn't matter how well you thought you had the thing tuned, there was still a good chance that the result that you got would be garbage, because there was no way to predict what the query content was going to be. And again, you in theory could go step by step and figure it out, but by the time you did that, you'd have a whole new batch of errors you had to deal with. One thing we never quite got right was bands and music. Take pretty much any block of text, and there's a decent chance that at some point, somewhere in the world, some combination of a band name, song title, an album title, and song lyrics would have a very similar set of words to that block of text. It was a completely unpredictable nightmare. For all of these projects, we understood what our code did, but there was just too much data changing to quickly predict the results. We could make the argument that we didn't understand what it was that was happening, but that just wasn't true. We just couldn't predict, given the huge amount of data we were working with, what the code was going to turn up. There are tons of other examples I could bring up, like high-frequency trading algorithms that operate on millisecond signals that are pouring in way too fast for humans to understand. But the thing to understand is this isn't unprecedented at all. In fact, one of the biggest challenges in software is figuring out how to deal with situations that are highly, highly data dependent at internet scale. So quite often I see situations like this where the people in one specialty of the tech industry just seem stunningly ignorant of the obvious similarities between what they're working on now and what is or has been going on in other parts of the industry for a long time. And it's a real problem because it causes people to reinvent the wheel when instead they could just make use of the solutions that have already existed elsewhere in the industry. Although, let's be honest, in this particular case, it might not be that they don't know about the existing precedents for what they're doing so much as they just want to pretend they're working on something world-changingly new to get more money, but they just aren't. This is a really hard problem, but it's just not unprecedented. It's not magic, and it's certainly not an indication that anything in the system is alive or thinking or any of that crap. I feel comfortable insisting that there's nothing actually intelligent in these systems because of four things. The first is Occam's razor. The simplest explanation that covers all the observations is most likely the correct one. We have a decades-old mechanism by which the unpredictability of the output of LLMs can be explained without the need for anything unprecedented. The second is what's called the Sagan standard. It's that extraordinary claims require extraordinary evidence. The claim that LLMs are unprecedented in the history of computing is extraordinary, and the evidence for that claim, at least so far, is not extraordinary at all. The third is that the people pushing this narrative have a huge financial incentive to make the public believe that these things are actually worth trillions of dollars. And lastly, because the AI industry has a history of just lying about stuff. I made a video on that here. So we will see if I'm right. I could be wrong, which you'll rarely hear the folks in the AI industry ever say. But so far, I'm just not buying the unprecedented argument. I don't see anything here that can't be explained by just searching a lossily compressed image of the web and randomizing the output. So don't let them fool you. If they want to claim their work is wholly revolutionary, they need to be made to prove it. Just pointing you at a chatbot is not good enough. Oh well. Thanks for watching. Let's be careful out there.